I'm going to talk about an effort to how small can you, how low can you go on hot water distribution systems and still have them work and still have them be safe. So the how low can you go slide, I'm working on a CC project with Gary Klein and Yanda Zhang. Analyze and recommend future code changes for hot water distribution systems. And we've got some other issues on there. So just to keep rolling quickly. This is the hot water, the water heating load in California. This is gas data from the 99 RAS, or the 2009 RAS. And of the gas load, water heating is by far, for all you zero net energy home people, you're probably seeing the water heating load is the biggest remaining load in the house. So that's why we're addressing it. I'm going to pick on California and actually a lot of Title 24. I hope Mozzie won't get too mad at me. And since we're focused on California and the Title 24 prototypes seemed like good houses to analyze to see what we could do. But if you dig into the Title 24, the prototypes, the one-story, 21 square foot house, it tells you it has 3 bedrooms. That 3 bedrooms is only for the water heating calculation, and I think some of the plug miscellaneous loads as well. But if you look at the floor plans, they don't tell you where the bedrooms are. They just tell you there's 3 of them. Since I'm worried about the hot water distribution system, I want to know where the bathrooms are, where's the kitchen, where's the laundry room, where's the water heater, where's the plumbing go? And it's not specified at all in there. So what do we model? Well, that's what we're trying to get at. Now, just to take a step back, this schematic of the domestic hot water systems, it's slide 5, shows sort of a cartoon figure of what you have to think about. Actually, the most important part is the people, because without people, your house is not going to use any hot water. And then there's the fixtures and the appliances, and that actually is done pretty well in Title 24 now. The red line from the water heater to the fixture is not done very well, and that's the part we're focusing on here. The water heater is actually done pretty well in Title 24 and in the calculations behind it. This is indoor residential water use. It's from the Residential End Use Water Study. They did 2 of them. They're done for water utilities, water conservation programs and water utilities. They metered like 10 houses, and well, actually they metered about 1,000 houses in the 99, and the 2016, I think they did 700 around the United States. Put a fancy data logger on the whole house meter to analyze the software to see what end use, which water went to what end use at 10-second intervals. So it's pretty good data. It's the best we have nationally. You'll notice between 1999 and the 2016 one, there were big water savings on toilets and clothes washers. That's when the federal standards tightened up on all of those. And you can see it in the data. This is field monitored data, so it's probably as real as it gets. What you don't see is big savings on showers and faucets. And that between the 1999 and the 2016 was when the shower head standards went into effect. They saved hardly any water. And Same on faucets. Dishwashers were pretty good. Baths use hardly any water, so not to worry about. But so we're trying to figure out come up with the tools to figure out how to rate systems to see where these losses are. The distribution of draws, slide 7, shows you this is some of the 1 day's worth of data from one of the studies they did in California, where they identified, this is the hot water use. It's the water and what time and how much and by what use. Showers are the big users. Faucets are all over. There's a lot of draws. It's very spiky. There's many hours where there's no water use. So it's very different from modeling than for modeling air temperature, because it's not hourly. It's nothing happens for a long time and then bing, 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 and then nothing, and then some more uses. The other interesting thing is most of you know that water gets less dense as it warms up, but the viscosity of water changes with temperature. You don't think of water as having viscosity, but when you're trying to figure out what the pressure drops are through fittings and through pipes, it's a big difference. Over the temperature range that we're considering, the viscosity of water doubles, or it's cut in half for hot water. It's twice what it is for cold water, which is a funny thing it's hard to think about and try to figure out how to put that in your models. This is some test data from the hot water pushing cold water out of pipes. The chart up on the right, the single pipe data, time is the time is to your right. The distance from the pipe, the start of the pipe is from the left, and the temperature's up and down. So you can see as you move down the pipe, it takes longer and longer for hot water to get there, and it takes longer and longer for the temperature to rise to the final temperature. And because it's an uninsulated pipe, you can see that as it gets down, as the hot water goes through, it loses temperature. That's for one pipe, but in a house, you don't have one pipe. You have a tree, a trunk and branches and all that. And this, what we're showing down on the left is a test rig where you can emulate what that is. You can build branches into that without having to string it all over your house, all over a house. And we'll be using some of that to make sure that the model we're building is representative. The spreadsheet modeling tool is trying to capture the effect that when hot water is pushing cold water through the pipe, it takes a while to get all the cold water out of the pipe, and then it takes a while, once all the cold water is left, for the remaining water to come up to temperature. And that's a fact that's caused, we think, by the water mixing as it goes through the pipe. So it doesn't, the hot water doesn't push it out like that. It sort of pushes it out like this and it gets mixed in. So you don't get hot, hot, or cold, cold, and then hot. You get cold, cold, sort of warm, a little bit warmer, a little bit warmer, and then finally hot. So that's what we're trying to get, and trying to use a few selected days with the draw pattern from Title 24, the prototypes from Title 24, where we've assigned the wet rooms and the locations and the structure of the pipes to be as realistic as we can, and then use this simple normalized curve to model the different sections of the pipe.
Question on that. Are you including the effect of the pipe heating of itself?
Yeah, yeah. I mean, this is, the curves are fit to data from a lab that was a pipe, sometimes, and measuring the temperature going in and the temperature coming out. So it includes the effect of heating the pipe and the pipe losing heat to the air as well.
And how recent the draw was at what the temperature like was left over from the test?
That's, well, the single pipe testing, we didn't do that, but the model is going to do that, because if you have a pipe that's full of hot water, or full of warm water that's only partly cooled off, you start at a higher temperature. So we're trying to capture that. We added rooms to the prototype floor plans. The standard layout was the one that Lynn was showing. The compact design, I think, was the one you guys showed too. So these are the same prototype, the same number of fixtures and fittings, just whether you design it stupidly, which unfortunately most of them are stupidly from a hot water point of view, or you squeeze them down so you don't have as much hot water in the pipe. Then you got to go through and size the pipe to determine how big the pipe is and how big you need, which depends on the peak flow and the friction losses of pipes and fittings that they're going to be measuring. And that'll tell you what size pipe you can do, all that. We're going to use the 2018 Uniform Plumbing Code and the alternate water demand calculator. The plumbing code sizing method is based on the Hunter curves, which was developed by Roy B. Hunter when he worked at the National Bureau of Standards, which is now the National Institute of Standards and Technology, under the Hoover administration. So that's the basis of the plumbing code. We're trying to bring it a little bit forward. Interestingly, to think about showers and the hot water use in a shower, it actually helps to think of it as two hot water draws. There's one that's a clearing draw where you cool out the cooled off hot water that's in the pipe, and then the part where you're actually showering. And if you do it that way, then the showering draw is when somebody's using it. That's the useful portion of the hot water. The clearing draw is complete waste. So you want to reduce the clearing draw and not affect the showering draw. The other hot water draws have other factors about them that we're assuming what's in Title 24 assumptions now. The faucets, all the draws are half hot, half cold. Clothes washers, all the draws are 22% hot. Neither of those assumptions are true, but they're probably close enough. Dishwashers are 100% hot, even though they're 100% hot, that's not the dishwasher getting hot water. It's the dishwasher using whatever water's in the hot water pipe. So if you can model that and figure out how much extra heat the dishwasher needs to have. And baths and showers, we assumed at a 105-degree mixed temperature. So in the winter, you're going to use more hot water and less cold water because the cold water is colder than in the summer. So trying to balance all that out. When you're measuring the performance of a hot water system, it's a question of what are the metrics you want to use. Yeah, I'm going to blow our lead. You want to use the temperature delivered, but that's not, it's not just energy. And what the energy simulation models count is energy, but for hot water, that's probably not all you want to know. Was the hot water delivered what temperature was it delivered? For showers, you want to know how long it took to get the hot water. You've got loads not met, or hours not, unmet hours, only this one, it's not hours, because nobody uses hot water for hours on end, except for a few teenagers we won't name. There's water wasted. The clearing draws are completely wasted water. There's the pressure remaining. In a simulation model, hopefully our model, we need to figure that out to make sure that you have enough water pressure to make your shower head work or your dishwasher. And another one is water age. For electricity, you don't have to worry how long it's been sitting in the wires. For water, especially water that you are potentially breathing in droplets of, you got to worry about how old it is. And these are contaminants, not like contaminants that Vertigo was talking about. These are biological contaminants. And there's this whole big issue of opportunistic premise plumbing pathogens. The one you've probably heard about is Legionella. There's some other nasty ones. As we're doing water conserving fixtures on pipes that are too long and too big, that means the water, in effect, is moving slower and slower through the pipes. And that means it's longer. The age refers to how many days it's been since it was treated at the water treatment plant. And so you're getting more and more pathogens coming out through the aerosolizer that's your shower head that you're breathing in. So our model is trying to figure out those sorts of things and compare how well a compact design with low flow fittings and small pipes, how well can that work? And I'm going to stop because before I get